everyone, my name is Kezia Aimee and my student number is 50032221187. And now I will be explaining for question number 49 and 410. For question number 49, a single server queuing system has a finite capacity K. The customers arrive according to a PP lambda and demand IID exponential mu service times. The server is subject to failures and repairs as follows. The server serves for an exponential theta amount of time and then fails. Once it fails, all the customers in the system go away instantaneously. The server takes an exponential alpha time to get repaired. While the server is down, no new customers are allowed to enter the system. If the system is full, the arriving customers depart immediately without getting served. Model this system as a CTMC. So for the first state is define the state space. Let xt represent the state of the system as time t, and the state space can be described like this, where n is the number of customers in the system, 0 to k, and the s is server status. For s equal to 1 is the servers when it's operational, and s equals to 0 when the server is down. Next, we define the transitions and rates. First is the customer arrival, lambda. The transition is 1.1 to 1 plus 1.1 for 0 less than or equal to n and less than k. Rate lambda. Second one, service completion. The transition is n.1 to n minus 1.1 for 1 less than or equal to n less than or equal to k. The rate is n mu. Each customer independently completes service. The third is server failure. The transition is n1 to 0.0 for 0 less than or equal to n less than or equal to k. Number 4 is the server repair. The transition is 0 to 0.1 and the rate is alpha. Okay, next step is the infinite generator matrix. The transitions above can be summarized in the generator matrix key, where each entry, key and s point empty, represents the transition rate from state ns to empty. The first one is key n1 point n plus 1.1. Lambda for n less than k is the arrival when server is operational. Number 2, key n1 point n minus 1.1 is n mu for n greater than 0 when the server completion. Third, key n1 point 0.0 is theta for all n greater and equal to 0 when the server failure. Number 4, key 00 and 01 is lambda when the server repair. And number 5, diagonal entries, key ns, point ns, and 0 sums are 0. And the states are ordered as 00, 01, 11 until K1. Next one is the system dynamics. A, customer dynamics occur only when S equals to 1 or the server operational. Customers arrive at the rate lambda as long as n less than k. Customers leave the system via service completions at rate n mu. B, server dynamics dominate transitions. Server fails at rate theta, sending the system to state 0.0. Server repairs occur at rate alpha, returning the system to state 0.1. No arrivals or service completions occur when S equals to 0 when the server is down. And the steady state equation to determine steady state probabilities P and S solve this equation, where lambda is the probability factor over all states. This model captures the queuing system's behavior with server failures and repairs. Okay, for question number 410, consider the 5-processor system described in conceptual problem 4.3. Suppose that the system maintenance starts as soon as the system crash. The amount of time needed to repair the system is an exponential lambda random variable at the end of which all 5 processors are functioning. Model the system as a CTMC. So the first step, we define the state space. Let xt represent the number of operational processors at time t. The first one is xt equals to 0 is when the system is down or in a repair. Next, for xt equals to k, for k 1, 2, 3, 4, 5, k processors are operational. Next, the system dynamics. The first one, the lifetime of each processing unit is exponentially distributed with rate mu. Hence, the failure rate of a single processor is mu. Second, when a processor fails, the system attempts to reconfigure as described in problem 4.3. If reconfiguration succeeds with probability C, the system transitions to a state with k minus 1 processors. If reconfiguration fails with probability 1 minus C, the system crashes and transitions to x equals to 0. And the third, if x equals to 0, the repair process begins immediately with an exponential repair time of rate lambda, after which the system fully resets to x equals to 5. And the rate matrix or the generator matrix, the CTMC can be described by the generator matrix key, where key ij represents the transition rate from state I to state j. The states are x, 0, 1, 2, 3, 4, 5. The transition rates are as follows. So the first one, from state k 5, 4, 3, 2, 1, or operational, a single processor fails at rate k mu. Upon failure, so the first one with probability C, transition to k minus 1 is successful reconfiguration, and with probability 1 minus C, transition to x equals to 0, or when the system is down. Number 2, from state x equal to 0, or when the system is down, the system repair at rate lambda and transitions to x equals to 5. So the rate matrix Q is as follows. So from the matrix, we can conclude that each row I represents a state x equals to I. Diagonal entries Q I are negative sum of the outgoing rates from state I. And the off-diagonal entries represent the transition rates from I to J. Okay, so that's all my explanation for question number 49 and 410. Thank you for your attention.